here we will look at a classification problem. So what is a classification problem? So we want to learn a classifier or estimate a classification function f(w), and this function has a set of parameters that we will discover later on, just in a bit. And what do we have here? So basically we have our training set. So these are our training samples. They have many features. So each training sample I belongs to RD, so it has D features. And we have two classes. We have the yellow class and we have the blue class, right? So for the yellow class, what we want to predict is the label. So for each sample, we want to predict the label of those samples, which is +1 for the positive class and -1 for the negative class. So our output here belongs to what? It belongs to -1, 1. Okay? So we have two possible outputs. So each label, yi, it takes either -1 value or +1 value. Now, let's look at this one. So what is the difference between a regression problem and a classification problem? So if you guys remember, in a regression problem, what did we plot in the x-axis? What did we have in the in the x-axis? Anyone? What did we have? So the input, right? So our feature vector x, right? And what is here? We plotted it against what? The output. Do we have the same thing here for classification? No. What do we have for classification? Slightly different. So in this case, what we want to learn how to represent the data by a line or by a curve. Okay, so we're learning how to represent the data by capturing the relationship between the target output that we want to predict and the input. So that's a regression model. Now for a classification model, what we're interested in is the features, the relationship between the features. So we have, for example, let's say we have an x, like each sample belongs to R2. So it means it has two features. And here we want to basically find, select first, imagine that we've gotten good features. First, like these two features, x1 and x2. When we plot the data, when we plot x1 against x2, we can see that they can be linearly separable. Okay? So there is a big difference between looking at regression and classification. So our goal in the classification problem is to estimate what we call a hyperplane. So this is a line in a one-dimensional space. In a higher dimensional space, it's just, or two-dimensional space, it's a line. In a higher dimensional space, it's a hyperplane. And this hyperplane, it's completely the opposite to the regression problem. We don't want it to be close to all data points. We want it to kind of separate these two sets, okay? So we want the distance from each point in one class to the hyperplane to be kind of far away and like distant from the other points, okay? So here in this example, our hyperplane has two parameters. So it has, the W and the B, and this is exactly the equation of a hyperplane. XTW plus B equals to 0, which means all points, x's, right, belonging to this hyperplane, they belong exactly to this hyperplane. They lie on this line, so they satisfy this equality, okay? So, right, so here we'll have two classes. So ideally, let's say we want to define a hyperplane separating between these two classes. What do we want to do? We want to put all the samples with label +1 above or on top of the hyperplane, okay, on this side. And we want to put all the blue ones on the second, like the bottom side, okay? So we would like the labels for all those points to be +1, okay? And the labels for these points to be -1. But in like, if you guys know, like in a all points that lie above the line of the hyperplane, or the hyperplane itself, they satisfy this inequality. So what do we have? We have here xtw plus b. They are positive, okay, strictly positive if they lie above the plane. And we know that all points that lie below the plane, they satisfy this inequality. xtw plus b, they're all negative. Okay? So, right, so next, what do we have? So, ideally, if we want to formulate this classification problem, we need to satisfy two conditions. What are these two conditions? First, if you look at this, for each point belonging to the positive class, we want it first to be on top of the plane, on top of the hyperplane, which means, let's call it xi, okay? So xi transpose w plus b, we want it to be positive. And we want also its label to be equal to 1. So we want its yi to be equal to 1, okay? As for the second points belonging to the second class, let's say I have a second point, like this point, for example. Let's call it xj. So I want xj transpose w plus b to be negative. And if its label is -1, okay? So these are the two conditions that will allow us to find the right points. Imagine if I have a wrongly classified point. For example, a blue point is classified by this hyperplane on top of this, on top of it. So it means, what does it mean here? It means that for this guy, I have it there. So it means that xtw plus b is positive. However, the yi is actually negative. Okay, so it's incorrectly classified, right? Now let's look at this more closely. So for example, we want, what do we want to do now? We want to think of a loss function that we can minimize for this classification problem. So I will walk you slowly and give you a minute to think about it. So here we have, for example, in this first case, we have a very nice separation between the red points and the blue points. But for the second case, you guys can see that our model, it has misclassified 2 points, right? So all points, let's look at the rule that we just defined. All points belonging to the above half side satisfy xitw plus b is positive, and the label is also positive. And what about the other ones? So we have the opposite. So xitw plus b is negative, and their label, okay, their label is negative. It's -1. So there is a trick here. So actually, interestingly, these two conditions, they are equivalent. We can write them in a compact form. How do we do that? Let's look at this. So this is the first condition for the positive class, and this is the negative class. And if we multiply by the negative of the label of each class, we will find a single inequality right here that will help us define our loss function to minimize. So I would like you guys to write it down. So I would like you to multiply these by the negative of the label and let me know what you find. So I'll give you just a minute to write it down, okay? So all you need to do is multiply both terms, like all of them, like, right, by minus yi. And same here, you multiply everything by minus yi. I'm going to give you a hint. So basically, you need to keep in mind that your yi is positive here. So the opposite is negative. But when it's negative, the opposite is positive. Okay? So which kind of equality you will find for both conditions? And remember, now we are looking at these two conditions that are valid for correctly classified points. So if one of them is violated, it means our points are incorrectly classified. So the first thing for this one, we're multiplying by what? We're multiplying by minus yi. So yi is positive, so minus yi is negative. So the first thing, we need to change the inequality symbol. That's number one. So here we'll have minus yi times xi transpose w plus b, strictly lower than 0. Okay? And for the second one, this is negative, so when we multiply by negative yi, it's positive, so they remain the same, so we have minus yi xi transpose w plus b. So what do you guys notice? We have exactly the same condition for all correctly classified points, right? So here, if a point is correctly classified, if we take the negative of its label, we take its feature vector, multiply it by our, our estimated w vector and the b, we will always find that it is negative. So this value will always be negative for correctly classified points. Okay? So now let's look at this. So this is what we exactly have. So here, we want all our training data to satisfy this. So if our classifier correctly classifies all the points, puts everything in the right side, then we will have this valid to all training samples. But it's not always the case, and we know that. It's a minimization problem. So our classifier in the beginning, when it's initialized, is going to make a lot of mistakes. And we need to know when it's making those mistakes because we want to correct them. Okay? So here, let's say this is, a trained classifier at some stage, so we're iteratively updating it, and we found that it has made 2 mistakes here. So these 2 points are incorrectly classified. So when they are incorrectly classified, what is the inequality or equality they satisfy? So do these 2 incorrectly classified points satisfy the same equality here? No, right? Because this is actually only valid. This is only valid for the correctly classified points. So this is the plus, the positive, and the negative, right? So what is the opposite of this one? The opposite of this one is minus yi xi transpose w plus b superior or equal to 0. So whether it's equal to 0 or it is positive. So if this quantity is positive or equal to 0, it means that our point is incorrectly classified. So now let's look at those. So for example here, let's say we have 6 training samples, 3 belonging to the positive class and the blue ones belonging to the negative class. And this is our estimated hyperplane. And we want to improve maybe the classification of this point that was misclassified. So this is, I think, here 1, 2, 3, 4, 5. So this is, y5 for sample 5. So sample 5 was misclassified. Okay. So it means like the model has made one mistake, and this mistake we can detect it because if we compute this for this point, if we take minus y5 x5 transpose w plus b, we'll find is positive or equal to 0. Now I'll give you a minute and I would like you to think about a potential, like a possible loss function that we need to minimize. Okay? So here, if we have basically a positive value, it means we need to minimize that positive value and bring it to something maybe negative or something like close to 0, because if our loss has many positive values, like let's say I sum over all those guys, just, hypothetically, but we're not summing here, but you can think about that, right? You're going to have a very large positive number, right? You have made a lot of mistakes, so you want to minimize them. So you want to make that basically go down to 0 or something like very low value. So I'll give you just, like 1 minute to think about it. What kind of loss we can potentially define based on these two conditions. So here we have two conditions. The condition for the correctly classified points and the condition for the incorrectly classified points. So even if you don't get something, it's okay. The most important thing that you try to think about the problem. So how do you do that? You might want to maybe draw a few cases, a few figures, right? So for example, let's say this is our first line. So this one will be positive, this is negative. So which means these guys will be considered as blue points, the top ones as yellow points, and then you need to optimize. So you need to decrease the number of mistakes you're making by changing the parameters of this line, the W and the B. Okay? Okay, so I'll just give you, like a possible solution to this problem. So the loss function that was defined, and which is we call the perceptron function. So this is exactly the function. It's a max function. It's a max function that has two variables, and it takes the max of 0 and this quantity. So let's look at this function first. What is the max of 0 minus 1? So if you remember, if this is negative, it means it's correctly classified, right? So max of 0 minus 1, it's 0, right? Max, for example, of 0 and minus 2.5, okay, it's 0. Let's say max of 0, and we have a positive value, which means the point is incorrectly classified. Let's say, for example, 15. It's 15, right? So you guys can see what is the pattern here. This function takes a 0. What is the lowest value that this function takes? It's a 0. So when it takes a 0, we have correctly classified points. If it takes a non-zero, a positive value, we have incorrectly classified points, which means that if we have a large value when we initialize our W and our B, right? We will have maybe 100 or 150. So our goal is to bring that 100 down to like something close to 0. Okay, so that's our goal. So this is what we call the max loss function. And here, so we will have a 0 for correctly classified samples and a positive value for wrongly or incorrectly classified samples. And this is how we define it. So this is what we call the perceptron or max loss function or cost function, so loss function. And we need to sum it over all training points. So it's just, we take the sum over the max function of the max function over all our training points. And the next step will be to minimize it, right? So we want to find the optimal W and B, which minimizes our new perceptron loss function. So let's look at this loss function, how how it looks like when we plot it. So this is also what we call the hinge laws or the rectified linear unit laws, which is like commonly used in like neural networks. So it's good that you guys just know about these terms, but we'll learn more about the hinge laws when we will discover the support vector machines. So here, what do you guys notice about our green max function? So this is exactly max 0s. S is a variable, right? So for values that are negative, it's always 0. And for values that are positive, we get exactly the same value. Okay? Now, this loss function has two issues. What are those? Can you think about two issues? Very good. It's not differentiable at 0. So here you cannot compute the tangent, okay? Which means to minimize it, if we want to use gradient descent to minimize it, our gradient should be, like the function should be differentiable everywhere, especially at 0, because we want to bring it down to that point. So here it's problematic. So very good. That's number 1. What is number 2? So let's say if we look at this, right? So what is L? If we take, what is L of 0, 0? The loss. So you're going to put like the sum, but max over 0, and what here? If your W takes a 0 and your B takes a 0, what do you get? We get 0, right? So this is problematic because we have already minimized this. We can't go below 0. So this max function, we say it has a trivial solution. So a trivial solution, when you're minimizing this, your algorithm might, just plug in easily the 0, 0, and then you would have no plane, like, right? But you would have reached the optimum. Because with, when you have W, the parameters of your plane are 0 and 0, right? You're not separating, but you have reached your optimum. You have reached your minimum. You're right there. So this is not good, okay? So when you have WB equals 0, you have your S equals 0, which is like just right. It's just that point, right? So these are the two issues. So it has the trivial solution, and then it's non-differentiable at 0. So as an alternative, how can we solve this problem? Alternatively, can you think about an alternative solution, like another loss function that we can define to solve this problem? Like tiny slope. So it's like you said, like maybe we can smooth the function around 0, like make it somehow smooth, like something like this approximating function. So here it's like it became smooth around 0, so we can compute the gradient, right? Good. So that's one possibility. So we need to think of a new loss function that approximates the max loss, the green curve. It looks very similar to it, but it is smooth, right, at this point. And what do you guys notice about this black line here? It also the S, so if we call it, for example, f of 0, it's different from 0, right? So even if we take, this trivial point that we took right there, we don't get 0. We still need to minimize to get our 0, right? So this curve actually somehow it solves both issues. So what is this curve? This is what we call the Softmax solution. Okay, so it's a smooth loss function, and it makes the max cost soft around this area. So it's like softer, right? And here, this is how we define it. So the soft of two variables S1, S2, it's the log of exponential S1 plus exponential S2. And here, we can see that it nicely approximates this function. So when we have the soft of 0s, so we have max 0s, we have log of, if we write it down, so what do we have? We have log of, exponential 0 plus exponential s, and this is 1. So 1 plus exponential s. So this is our function. This is our new function. And then we need to define our loss. So this is our previous loss where we had the max. We cannot really solve it because computing the gradient is not straightforward. So we use the soft max, and we replace it right here. So this is our softmax function. So log of 1 plus exponential and this quantity right there, our multiplication condition. And here, what do we have? We notice that the W, which is a vector, it's a d-dimensional vector, and B, which is a scalar, they're not a trivial minimum anymore of this, softmax perceptron loss function to minimize. So we kind of circumvented that problem. And here you can see how we can come up with new loss functions. So if you define a loss function and you see it's quite problematic at some points, then you might want to think of another loss function that can approximate it and give you better results. Okay? Right, so here, this is what we need to minimize. So how do we minimize this? So you guys know the steps. So we use gradient descent or Newton's method, because this function is what? It's a convex function, right? It looks upward. So it's convex. It's a convex function. So it has an optimum. So here, it's very nice. We can either use a Newton's method or gradient descent, right? And something interesting about this softmax loss function, we also call it the logistic regression for classification. Why? Because when we compute the gradient and the Hessian, when we derive those mathematically, we find the sigmoid function. So the sigmoid, you remember, it's like, the hallmark of logistic regression. This is why we call it, kind of logistic regression, okay, for classification. We also call it the log loss because we have a log here. So it's a log loss function, and this is the log loss function for the support vector machines, which we'll look at later on, okay? So these are two examples where we applied the softmax to two different cases. So in the left plot, we see that these classes, the blue points and the red points, are nicely separable. They're non-overlapping, so we have a nice line, a nice hyperplane separating them. But in this case, even with some overlap right there, it's still, still the softmax had a good estimation of the separating plane too, okay? But there are different issues. So if you want to think about how can we improve this further, right? How can we improve the classification for the overlapping points? So this is something else you might try to think about, and maybe define a new loss, or maybe think about how you can move your points before thinking of the loss. So maybe you can deform your space, you can move your points to make to decrease the overlap and then do the classification, okay? Great, so let's look at the prediction step. How are we going to predict? So it's quite simple. So we have, let's say we have a new point. So this is our new point. New testing sample in this example, it has only two features, x2 test. Okay, so what we need to do, we have our optimal parameters that we estimated by minimizing the softmax function, and then we just need to look at the sign we get by computing this. Remember, because if the point has a positive sign, a positive label, so it lies above. So if this is positive, it means it lies above the separating hyperplane, right? If it lies below, then it is negative. So in this case, when let's say we take the sign of this. So the sign, it means, what is the sign of this quantity? Is it positive or negative? So if it's negative, then we know it should be somewhere around there, okay? So if this is the label, the predicted label for our testing sample TS, YTS test, okay? Great. So to compute the accuracy, there are many, there are different metrics, but here in a very, very simple way, we can compute the number of correct predictions and divide it by the total number of testing samples. That's it, and multiply by 100 to get a percentage, maybe like a 70% classification accuracy rate. Okay? Great, so let's look at another case. So this is the last part here. So for example, what do you guys notice? So previously, all we cared about is to find a good line that maximizes the separation, that just separates these two sets, okay? Now what we want to do, we want to make the optimization more constrained, which means we want to separate these, the blue ones, the yellow ones, these guys, and also the blue class. We want to disentangle the blue from the yellow class, but within a margin. So I want them to be far away. So I don't want them to be close to this zone. So I want to maximize the margin, the space between them. Okay, so this is another idea, that I don't want just to classify, I just want, or separate, but I want to separate them well, like I want them to be far away, okay, within a margin here. So let's, so in this case, imagine what we have. So this is the case right there. So we have our original hyperplane, so this is the original hyperplane, and the equation of our hyperplane. And then we want to define what we call a margin or a buffer zone. And here we want these classes to be separable within a +1 in this direction and a -1 in the other direction. So the size of the margin here, it's equal to 2. Okay? So in this case, what we do is very simple. We just shift the hyperplane up by +1 and shift it down by -1. And we want to solve for this new constraint. Okay, so what is the new constraint? I want each positive sample, okay, belonging to the +1 zone to satisfy this condition. So what is this condition? I want it to be above this new boundary. So this new boundary, it's xtw plus b minus 1 equals to 0. So this is the equation for this hyperplane, okay? So I want all my points to be above this hyperplane. So this is the equation for the hyperplane, right? So I want it to be positive. And here, if we can write it down this way. So we move the one to the other side. And I want their y's to be positive. And for the blue ones, it's just the same thing. So we have the equation for this hyperplane, xtw plus b plus 1 equals to 0. So I want this basically to be negative because I want these blue points to lie below this hyperplane. And I want their labels to be equal to -1. So this is a new condition. And this is exactly what we call the margin perceptron. Okay? So the margin perceptron, we have these two new conditions, right? And if we multiply by their respective labels, we get this unified inequality for both, correctly classified points above and below the margin hyperplanes. Okay. And right here, it's just, it's simple. So if you multiply by -1, so we put the 1, we shift the 1 to the left side, multiply by -1, and we get this new condition. So we want this quantity to be negative. But here, you guys need to know this, that it's smaller or equal to 0. Okay? Why is that? Because if you look at this, before, we allow points, so we allow points here to lie on the boundary. So they're still far away from the blue one. So that's okay. So they can be equal in this case. Okay? So it's like we have this new condition. And then what is it that we're maximizing if we write the max margin perceptron? So it's the 0, but we replace the second term with 1 minus. Well, it's just we added a 1, right? So it's quite simple. So this is what we had before. We had -yi xit w plus b, right? And we did the +1. And you can see the +1, it changed many things. So it made our classes separable within this big buffer zone. Okay? And the next step would be to minimize this function. So how do we do that? So we minimize our w over w and b, but we need to sum over all our points. And this is our new margin perceptron loss function. So what do you guys notice? We have this function is also has some problems, right? So it's not soft. It's not differentiable everywhere. So we need to perform exactly the same steps. So what we do, we take the soft, what we call the soft, we soften it, we make it softer and differentiable. So we take the log 1 plus margin condition, okay? And that's what we have. Or there is another loss function that we can also define, so which we call the squared margin perceptron. So we only square the max. So when squaring the max, both become differentiable, and also both they are convex. So these two functions are convex. So these are two different losses that we can use for the margin perceptron. Okay, so let's look at this case. So here we have, after defining our function, we compute the gradient descent, right? We perform the gradient descent, and we notice that for the squared margin loss, if we initialize our hyperplane at different positions, we always end up with a good estimation of the optimal hyperplane. And even in the case where we have some overlap between these two classes, we have a good hyperplane using the squared margin loss function. And let's look at this one. So I'll give you a minute here. So this is the last part. I'll give you a minute here, and I want you to look at those curves and interpret them. So here you will compare the performance of these two losses. So the first one is the Softmax. So this is, without the margin, and this one is the squared margin function where we added the +1, okay? So what do you guys notice? So this, we ran basically a classification algorithm on 3 different data sets. So breast cancer data set, spam data set, and face detection. So this tells you, it looks at an image and tells you if it has cancer or not. This one, it looks at an email and it tells you if it's a spam or not. And this one, it detects faces. So it looks at objects and tells you it's a face or not. Okay? So it's a binary classification problem. What do you guys notice when you compare the performance of these two different perceptrons? So here, what do we have? We have the number of misclassifications, and this is the iteration of the gradient descent. So we're iteratively trying to find the optimum, right? So we're trying to minimize the loss, and minimize the loss means getting less mistakes. It means we are decreasing the number of the misclassifications as we iterate the gradient descent algorithm, okay? So in this case, what do you notice? For the first case, we have the first loss, the Softmax gave us this error, and the other one is like the squared margin. We have only 26 errors. So which one is best in this case? The squared margin, right? In the other case, right here, what do we have? We have the opposite, right? That's quite interesting because this is, real world machine learning. You can develop an algorithm, you can test it on one data set, and then it doesn't work as well. It doesn't work very well on a different data set. So you need basically, you need to find sometimes the best method that works on your data. And this is a problem because you want to show that your method that you devise is generalizable, which means you can apply to solve different problems. So that shows that your method is strong and it's generalizable. But here, you might not get always the best performance achieved by your method, and this is quite problematic generally in machine learning methods. So here you can see that it's the Softmax Softmax that gave the best results right here. And for the third case, they're almost similar, okay? But as you guys notice, all of these methods, they converge within 10 iterations. So the number of mistakes is constant, so there is no change. So it means like you're like, even if you're still optimizing, your loss is like, changing in a negligible manner, okay? Any questions?